Bismillahirrahmanirrahim. Assalamualaikum dear students. I hope you all are fine and in the best conditions of your health. So in today's lecture we shall discuss about some examples of stereospecific reactions for the course of organic reaction mechanism, right? So the key concepts which we shall discuss in this lecture are the stereospecific reaction and the stereoselective reactions, right? So briefly, just as we have seen the previous lecture on the stereoselectivity, we saw that whenever there is reaction and whenever there is a choice in a reaction, so whenever there is a choice and among the choice there is some preference, then there comes the question of selectivity, right? So suppose that if we have a reaction that yields two products and the two products are formed in different amounts, then the product which is formed in greater amount is said to be preferred one, because the reaction mechanism is preferring that product over the other product, right? So we say that the product that is being formed in higher amount is a selective product because it's preferred one. Similarly, if two different reactions result in formation of a single product, however, the reactants react at different rate. For example, one reaction yields the product at a faster rate while the other reaction yields the same product but at a slower rate. Then the reaction that yields the product in the faster rate of reaction, that will be considered as a favored reaction and that reaction will be selective, right? We also saw that selectivity is of two types when we are considering the stereoselectivity. The reactions are enantioselective or the reactions are diastereoselective. So for example, if in a reaction we get two enantiomers, and if the two enantiomers are formed in different amount, then the enantiomer that is being forming in higher amount, that enantiomer will be considered as the preferred one, and we say that this enantiomer is selectively formed in more amount. Right, so that's selectively preferred. Since that's a stereoisomer, therefore the selectivity will be considered as stereoselectivity. Right? Similarly, when a reaction yields two diastereomers and the diastereomers are formed in different amounts, then the diastereomer that will be formed in more amount will be considered as the selective product because it's formed in a greater amount. Right? So we have considered about selectivity, and in today's lecture we shall discuss about some stereospecific reactions. Right? So the difference between selective reaction and specific reaction is that the stereoselective reactions occur when there is some option, right? While the stereospecific reactions occur when there is no other option, and the formation of the product is determined entirely by the reactant. So if configuration of reactant is this one, the product should be this, right? So without any exception. So in reactions that will result in inversion of configuration, so there is no other option than inversion. So such reactions are considered as stereospecific reaction because there is no other option, right? So difference between the specific reaction and the selective reaction is that in selective reaction we have options, and these options result in formation of product at two different amounts. While the specific reactions, there is no other option, and the indication of a reaction to be specific is that it will result in formation of only one product. Right? So let's consider a few examples of stereospecific reactions. So here we have, you can say, a secondary alkyl halide. Right? Here is the secondary alkyl halide. And you can see here we have an iodine. So iodine is a larger size halogen and it's very good leaving group. Right? So here we have a good leaving group, and here we have a larger size atom as well, so which can stabilize itself. So now what happens that here we have a hydroxyl atom. So hydroxyl atom is acting as a nucleophile here. Right? So you can see that nucleophile is hydroxyl atom. So here we have OH, and it's acting as a nucleophile here, right? So now this OH has two options. Number one, this OH can attack from the same side as of the halogen, right? So hydroxyl can go on the side in which this iodine is present and attack on this carbon. The second option is that instead of doing so this hydroxyl attacks from behind the sign of the iodine. So hydroxyl has two options. So what side will be preferred? You can see that iodine has a larger size, right? And iodine is also a good living group here. So this iodine has larger size and greater electronic density because this iodine is a halogen, and we know that halogens have 3 lone pairs of electrons, right? If this hydroxyl were to attack on the same side as this halogen, you know that this is our oxygen, so oxygen is electronically rich and oxygen has 2 lone pairs of electrons, right? So if hydroxyl were to attack from this side, then what happens that there will be repulsion between the electrons of this iodine, which is quite larger size atom, and this hydroxyl, which is also electronically rich center. Right? So in order to avoid this repulsion, what happens is that hydroxyl, instead of attacking from same side as that of iodine, so hydroxyl does not attack from this side. Instead, hydroxyl attacks from the side in which the hydroxyl group is at maximum distance from this iodine. Right? So this angle between the hydroxyl and iodine is 180 degrees. Right, so this hydroxyl groups attack from 180 degrees to this iodine, so that the repulsion between this hydroxyl and iodine is minimum. Right, so in this way, when it happens, what we'll get? So we have a hydroxyl which is attacking from maximum distance to that iodine, because both are electronically rich and both show repulsion to each other. So this hydroxyl is attacking from behind side, and this iodine is leaving like that. Right? So hydroxyl can never attack from the same side as that of iodine, right? So this is no option. So there is only one option for this hydroxyl to attack, and that side is from the behind. See? So we have no other option. So since we have no other option, so this reaction will be called as specific reaction, and since we are dealing with a stereoisomer, so this reaction is considered as the stereospecific reaction. You can see that here, as a result of attack of this hydroxyl, right? So see, hydroxyl is attacking from backside, so iodine is leaving here. So we will only get the inversion of configuration. You can see here the iodine was on your right side, but in the product, the attacking group has attacked on the left side, right? So there is no other option. So what we have starting material of R, and the product will have configuration which is inverted, that should be S. So in this reaction, we never get R from R, we always get R from S, right? So the stereochemistry of the product is dependent on the stereochemistry of the reactant. So if reactant is R, the product should be S, and if the reactant is S, the product should be R, right? So in this specific reaction, there is no other option but of inversion, right? And the reason for that is this iodine. Right? So iodine is a very good leaving group and very large size of that. Let's consider another enantiomer of this isomer. So here we have R isomer. Let's consider about the S isomer of the same compound. Again, we have an iodine here, the same role of this hydroxyl. So this hydroxyl will attack at the nucleophile. So this should go only from behind the side. Right, so this hydroxyl will attack at 180 degree to this iodine. So as a result, what happens that inversion of configuration takes place. So you can see that reactant has S configuration, so the product should have R configuration with no exception. Right? So this is stereospecificity. So in case of stereospecific reactions, we don't have any option, and the stereochemistry of the product is always dependent on the stereochemistry of the reactant, right? So this reaction is stereospecific, and it always proceeds via inversion of configuration. Let's consider another example here. So here you can see we have a hydroxyl group and we have this alkyl halide here. So here the product is a E alkene, right? So alkene with an E configuration. So it means that we are carrying out dehydrohalogenation here. So what happens that here the role of this hydroxide is to act as a base, right? So this hydroxide will act as a base, and this base will pick up a proton from here, right? So when you pick up the proton from here, what happens is that this proton, right, in order for E2 elimination to occur, so always remember that this proton and this bromine should have an angle of 180 degrees, right? They should be anti-periplanar, right? So if hydrogen is on this side, then the PR should be at an angle of 180 degree, right? You should have opposite configuration here, right? So in order for this reaction to occur, this hydrogen and this alkyl halide should be opposite to each other, right? Should be anti-periplanar to each other, means should have an angle of 180 degree, right? So here this angle is satisfied because this hydrogen is above the plane and this Br is below the plane here. So what happens, that configuration is the correct one. Here the hydroxyl will pick up this proton. This proton will donate its electron pairs to this carbon, and this bromine will leave in order to stabilize the valency here. So you can see here that when this bond is formed, then these two phenols are opposite to each other. See? So these two phenols are opposite to each other. So here we only get the E isomer. We never get the Z isomer here. Because in case of Z isomer, this hydrogen and this bromine will never be anti-periplanar to each other. Right? So in case if you have to form the Z isomer, then what happens that this bromine, this phenyl group, should be on the same side as that of phenyl group. So in that specific case, this hydrogen has to go in below the plane here. Right? So hydrogen cannot go below the plane because we have to maintain an angle of 180 degree. Right? So we only get one isomer, we only get the E isomer from this reaction, we don't get the Z isomer. Reason why? Because we need to have an anti-periplanar transition state. So if we cannot get an anti-periplanar transition state, E2 elimination cannot occur. Right? So here again we don't have any other option, so the reaction will be considered as stereospecific. So why stereospecific? Because the reaction has to assume an anti-periplanar transition state. Right? So without any anti-periplanar transition state, the reaction will not occur. So this reactant will only yield the E product. It cannot yield the Z product. Right here, so this is an example of stereospecific reaction in which we don't have any other option. Let's consider the example. So here we have already a chiral center here. Right? So we have a chiral center here and we have a hydrogen over palladium here. So what's the role of hydrogen over palladium? So this hydrogen over palladium is a reagent, and this reagent causes addition of hydrogen to a carbon-carbon double bond. Right, so we have carbon-carbon double bond here, and this hydrogen should go on this carbon and the hydrogen should go on that carbon. So as a result, we'll get product in which this CH2 group will become a CH3, and here we'll get a hydrogen here. Right? So we'll get a single bond between carbon-carbon here. So what happens that when we carry out this reaction in the presence of acetic acid, we get two isomers, and you can see here we have two stereogenic centers here. Alright, so you can have the configuration of this stereoisomer. You can see that here we have, this is first preference, right? So this carbon will have first preference, this will have second preference, and this methyl will have the third preference. And you can go from the first preference to highest preference. So this is clockwise, right? So the configuration of this carbon is R, while this carbon, the other carbon, you can say again we are assigning the configuration. So this carbon will be 1, this will be 2, and this carbon will be 3, right? So the configuration should be right. So this is anti-clockwise. So one of the configuration is R, while the other configuration of this carbon, right here we have R configuration and other we have an S configuration in that center. So in the other isomer we have R configuration, and let's consider this isomer. So here you can see that we have the methyl here and the hydrogen here, right? So since this hydrogen is not below the plane, so apparently what appears, the configuration will be reverse of it. So let's consider the assignments 1, 2, and this is 3. So now we get the configuration here. So this is appearing to be anti-clockwise, but since the hydrogen is not below the plane, so although it's appearing to be anti-clockwise, so the isomer will be right. See, here you can see that this is a combination which is not mirror image of each other. Right. So this isomer has a configuration of R and R, while this isomer has a configuration of R and S. Right. So these are not mirror images of each other. If these are mirror images of each other, then if one has the configuration of RS, the other would have configuration of SR. Right. So these isomers are mirror images, SR and RS. But if we have configuration of RS and RR, so these are not mirror images of each other, right? So it means that the products which we are getting are the diastereomers. They are not enantiomers, right? So this reaction is yielding to enantiomers, and you can see that the cis enantiomer, why we are calling it cis, because the same groups are on the same side. Although this is a single bond, but the terminology of cis trans is also applicable for cyclic system. So here we have two methyl groups, and the two methyl groups are on the same side. So these are cis, and here the methyl groups are on opposite sides. Here is above the plane, and here is below the plane. So this is the trans configuration. So you can see here that the cis is forming in more amount, while trans is also forming, right? So since we are getting two products, and we are getting two products in different amounts, so this is not a specific reaction, because a specific reaction always yield one product. So here this is example of diastereoselective reaction, right? So we are getting two diastereomers in different amount from the same reactant, right? Let's consider another example. So here we have an alkene, and to this alkene we are adding a bromine here, right? So you know that bromine addition occurs. So in the first step, the pi electrons will attack on this bromine, and the second bromine will leave out here. So what we get a carbocation here and a Br here, right? So this carbocation is secondary, but if we were to attach the bromine on this carbon, we would have got a primary carbocation which is not stable, right? So bromine is getting attached on this carbon in order to form a more stable secondary carbocation here. In the next step, what happens that instead the second bromine attacks as a nucleophile, this bromine attacks internally on this carbocation here, right? What happens that this bromine is attacking on this carbocation, and it's forming a three-membered transition state in which bromine is having a positive charge here, right? So now we are getting a cyclic bromonium ion, right? So this is cyclic system, and we have a bromine, but bromine is having a positive charge. So this onium word means that we have a positive charge, and brome means we have a positive charge on bromine, right? So name is indicating the bromine with a positive charge here. Now in the second step, what happens that this three-membered ring is a highly strained system, and it has to get the ring opening here, right? So we are having a bromine here. So this is the bromine which leaves in the first step of this reaction. So this bromine has two options. Number one, this bromine can attack from the same side on which the bromine is attached, and the other option is that bromine attacks from behind, right? So in case if bromine attacks from the same side, you can see there this bromine is a larger size atom, this bromine is a larger size atom, so both are halogens and have 3 electrons, 3 lone pairs in the outermost shell. So these electrons will repel each other, right? So in order to minimize this electronic repulsion, what happens that bromine approaches this carbon at a maximum distance, so that this bromine and this bromine are at a maximum distance, right? So this bromine has to avoid the repulsion. So this bromine cannot come from above side, it will always come from behind the side, from the lower side, right? So this bromine has no other option but to approach from the back side, right? So since there is no other option, this reaction is an example of specific reaction. And since we are dealing with the stereoisomer, therefore this is stereospecific reaction. So here what we see, you can see that the two bromines are added in trans fashion, right? This is anti-product. So you must know about some terms. So you must know about, in case if we have a carbon-carbon double bond, and if two groups which are same are on the same side, we say this is cis, right? So this is a cis isomer. This is cis. But in case if we have a carbon-carbon double bond and the same groups are on opposite side, you know that this is a trans thing, right? But in case if we have a single bond and on the single bond the same substituents are on same side, we say this as syn, right? This is syn, SYN. But if we have a single bond and along which the same groups are on opposite side, this is called anti, right? So if we have same groups on same side of carbon-carbon double bond, this is cis. Same groups on opposite side, trans. So if we have a single bond and the same groups are on same side, this is called syn. While if we have a single bond and the two groups are on opposite side, this is called anti. So here you can see we have a single bond and the same groups are on opposite side. So this is anti-product. So this reaction is stereo-specific reaction because we only get the anti-product. We don't get the syn product, right? So there is no other option but to get a syn product, to get an anti-product, right? So since there is no other option, therefore this reaction is an example of stereo-specificity. Again, we have another option, we have another example. So here you can see we have ketone and two different groups are attached, methyl and a phenyl group, and third we have an oxygen. So in this case, you know that this carbon is a chiral center, is a prochiral center, because if we add another group to this carbon, so what we'll get? We get a chiral center. So this carbonyl is a prochiral center. It can result in formation of a chiral center, right? So here we have sodium borohydride. So what the sodium borohydride does? Sodium borohydride acts as a source of hydride ion, right? So this sodium borohydride will act as a source of hydride ion. So here we have hydride H negative. So this hydride has to attack. Now this hydride can attack on this face or it can attack from the below face, right? Suppose that if hydride attacks from above, right, from this face, you can see about which face is that. 1, 2, 3. So this face is the 5 face, right? So this hydroxyl is attacking from the 5 face. Means this hydride is approaching from above face. So what happens if hydride is approaching from above? The hydroxyl will go below, right? So in that specific case, we'll get this product because hydroxyl is going below and hydride is approaching from above. But if the reaction proceeds from the side face, meaning the below face here, then in that case, if the hydride is approaching from below, the hydroxyl group will move on above side here. So this product will be formed when this hydride H negative is attacking from the D face, right? So you're getting two products, and here you can see the two products are formed in 50-50 amounts. There is no preference, so this is not a selective reaction. It's also not a specific reaction as well, right? It's not stereospecific, not stereoselective. This is a non-selective reaction because the two products that are formed, they are formed in 1:1. They are formed 50-50. There is no preference. So now we're going to understand why this reaction is yielding the two products in 50-50 amounts. The reason lies in the transition state. So in case if the reagent, if your hydride is approaching, so if the hydride is approaching from this side here, right? So if the hydride is approaching from this side, let's draw it out, right? So this hydride is approaching from this side. What happens? This is hydrogen which is approaching, and this hydrogen is part of this sodium borohydride. This hydrogen is attached to this boron. This boron is electronically deficient. This boron is having attraction to this oxygen here. So we get a transition state like that. Right? right? You can see that this boron is attacking on this right side of the carbonyl. So this is a re-attack because this is a re-phase here, and we get a transition state. But let's suppose that if this boron group was attacking on from the psi phase, so if it were to attack from the psi phase, you can say here, so we have this carbon and we have a methyl here and a phenyl here, right? And here we have a boron, and to this boron we have hydrogen, right? So this is the transition state in which boron is showing attraction for the oxygen and the hydride is showing attraction for the carbon. So you can see that both of these transition states are exactly the same. They have the same energy. Since they have the same energy, so the mechanism does not distinguish between them. As a result, both products are formed in 50-50 amount because the transition state is equally stable. However, if the transition state is not equally stable, we get two different products. Right? So you can see here the basis why two different products are formed in different amounts or in the same amount, because all is related to the transition state. So if the two transition states have equal stability, then the product will be formed in equal amounts. But if the transition state have different stabilities, then the transition state which has lower activation energy, that will result in formation of a product in more amount, while the transition state that has higher activation energy, this transition state will result in formation of a product in lesser amount. So let's consider another example. So this is again an example of addition of this borane to the carbon-carbon double bond. So previously we had a carbonyl-carbon, now we are having a carbon-carbon double bond here. Right? So the hydride is attaching on this hydrogen and the boron is attaching on this carbonyl. Right? So we only get exclusively this product, which is syn product, because the groups are adding on the same side. So whenever borane attaches to carbon-carbon double bond, the hydrogen and boron are added on the same side. Reaction is concerted. We never get a product in which anti-addition occurs. So this hydrogen and the boron always adds on the same side. Exclusively syn addition. Exclusively means we get only one product. There is no other option. Since there is no other option, so this reaction will be example of, yes, it's an example of stereospecific reaction, right? We only get the syn addition exclusively, we don't get any anti-addition. Now consider that we have a chiral center here. This is a chiral, but this is a pro-chiral center, because if we add another atom on this carbon, so that will become a chiral center here. Right, so what we get, we firstly add borane BH3 to this molecule. So you know that boron should go to the carbon. That is less substituted here. Right. So what happens? Let's consider that this is the boron, and let's consider we have a boron, and the boron should always go to the carbon, that is less substituted, while hydrogen should go to the carbon, that's more substituted here. In the next step, we are adding the hydrogen peroxide. So what hydrogen peroxide does, hydrogen peroxide replaces this boron. Right, so this hydrogen peroxide is replacing the borane BH2 group with the hydroxyl group. Right. So ultimately what we get, so in this reaction, in this specific reaction, we get two products. One in which both hydrogen and hydroxyl are on the same side, and they're above the plane, and the other in which both are on the same side and below the plane. So this reaction is stereospecific. Why stereospecific? Because the addition is always syn addition, but the products are forming in 50-50 amount, because the transition state has equal stability in both the cases. Right? So this reaction results in two enantiomers with 0 EE, because no enantiomer is formed in excess. Right? So they are formed in equal amounts, so the enantiomeric excess is 0%. Right? So all the reaction is specifically syn. This stereospecifically syn addition, because we are only getting the syn addition. So this hydrogen and boron are adding on the same side, but what we get the two products in 50-50 amount and with 0 enantiomeric excess. Why? because the two isomers, there's two options, because the both groups can add on the same side either from below the plane or the above the plane, right? And since both have equal possibilities, so that's why this reaction, although the addition is stereospecifically synth, this reaction is giving you two products which are in 50-50, so the enantiomer success will be 0%. Another example here we have again a carbonyl system, and you can see this carbonyl system is unsymmetrical. So here we have a chiral center, and we are adding a hydride on this chiral center here. So this hydride can approach either from above the plane or from below the plane, right? So if this hydroxyl is approaching from above side, I say that here we have a hydroxyl group, and this hydroxyl group is this hydride group. So this hydride is approaching from this face. What happens if the hydride is approaching from above, the hydroxyl will go below. So this product will be formed when the hydride is approaching from above the face. But in case if this hydride is approaching from below face, the other face, then in that case, since the hydride is coming from below, the hydroxyl will go on the above side, like this one. So this product will be formed when hydride is approaching from above side, right? So we're getting two isomers because there's two options, right? So since there are options, you cannot say this as specific reaction, right? So we are getting two isomers. We are getting the isomers which are diastereomers. How we can say diastereomers? You can just see the configuration. So one isomer is 1R2S and other is 1S2S. These are not mirror images of each other. If they were mirror images, then if one has configuration 1R2S, the other would have configuration of 1S2R. They should have mirror images, but these two isomers are not mirror images of each other. So this is why we say that these two isomers are diastereomers. Let's check the stats. So in case when you are using the lithium aluminium hydride in this hydride, right? So this hydride is the hydride donor, it's a small size molecule. Then in that case we are getting the both isomers, and one isomer is formed 76%, other is 24%. You can see there is some diastereoselectivity. You see, one of the isomer is dominating. This isomer is forming a larger amount, while this isomer is forming a lesser amount. But when you are using a bulkier size hydride source, right? This is bulkier atom. This is diisobutyl aluminium hydride, and we call it as dibar. So when you are using this strong hydride source, which is a large bulkier source, then in that case you can see that only this product is forming and this product is not forming at all. So when you are using the dibar is exclusively yielding only one product. So with dibar there is no other option. But with lithium aluminium hydride there are two options, right? So you can see that reaction with dibar is stereospecific because it is only preferring one product, while when you're using lithium aluminium hydride you're getting two products, but they are forming in different amounts. So the reaction is stereoselective when you are using lithium aluminium hydride. But when you are using diisobutyl aluminium hydride, when you are using dibar, then you get only one product 100%. You get an exclusive product, right? So it means the reaction is stereospecific when you are using dibar, and the reaction is stereoselective when you are using lithium aluminium hydride. Right? Let's consider why these two isomers are formed in different amounts. Why the reaction is favoring the production of one isomer while the other isomer is formed in lesser amount or is not forming at all. Right? So let's consider this isomer. This is 2S-isomer, you can see. So suppose this lithium aluminium hydride, this is aluminium hydride, right? So whether this is lithium aluminium hydride or this is the dibar, right? In both cases we have hydride with hydrogen here. So this aluminium will get bonded with oxygen, and this hydride is being transferred to carbon here. So let's consider that this aluminium is approaching from below the plane, right? So this is approaching from above this methyl. So methyl is above, you can see here. So in that specific case, though the repulsion between aluminium hydride and methyl is minimum. So since there is minimum repulsion, so this transition state will have lower energy. So the activation energy for this transition state will be lower because the transition state is stable. But in case if this aluminium hydride is approaching above side, here you can see this methyl and aluminium hydride will have repulsion. Because of this repulsion, the transition state will become unstable and will require larger energy. It will have higher energy barrier, right? Because of the higher energy barrier, so the transition state formed for the case in which the aluminium hydride is approaching from the same side as in case of methyl, so this will have a higher energy, right? So since it has higher energy barrier, so that's why the product that's forming from this, that will be formed in lesser amount because the energy is higher. Now suppose that the aluminium hydride is approaching from above, but this aluminium hydride has a bulky size like this one. So since it has a bulkier size, it is not possible for aluminium hydride to approach from the front side because it's a very bulkier group. And since the repulsion will be so much between this aluminium hydride source and this methyl, the system will become too much unstable. Therefore, when you are using this diisobutyl aluminium hydride, this reagent never approaches from the side on which methyl group is present. It always approaches from the side in which methyl group is opposite to each other, right? So that's why when you are using DIBA, you get only the product in which the transition state is more stable because of less steric interactions, right? So you can see here the reason that why when you are using lithium aluminium hydride, then the product is forming in more amount, right? And both the products are forming, right? And there is some selectivity, and the selectivity is because of this methyl group here, because when the aluminium hydride is approaching from the above, so there is repulsion between aluminium hydride and methyl. But when the aluminium hydride is approaching from below the face, away from the methyl group, there is no repulsion. So this is the relative stability of your transition state. If the transition state is more stable, the energy barrier will be low and the product will be formed in more amount. But if the transition state is highly unstable, the energy barrier will increase. As a result, the product will be formed in lesser amount. I hope you have understood this lecture well and you have clear concept about the stereospecific reaction and stereospecific. That's all for today.